As you can see, the goal of this video is to find the x-intercept, y-intercept, and vertical asymptotes of a rational expression. So, as you can see, this rational expression is written in standard form right now, and we're going to focus particularly on factoring this and identifying the y-intercepts from this slide. If you're more interested in finding the x-intercepts and vertical asymptotes from factored form, just fast forward to the next slide and you'll be able to find the standard expression written in factored form. So, to begin with, we are going to first need to identify the y-intercept, and standard form is actually a whole lot better to find the y-intercept with, because all we need to focus on are these last digits out here. So we're looking for our constants, and you might remember that a constant is a number without a variable. So these two values can be divided. 12 divided by -6, our y-intercept is going to be 12 divided by -6, which simplifies to -2. It really is that simple to find the y-intercept, and as we discussed earlier, it relates all the way back to linear expressions, or excuse me, linear equations as well, where if we have something like this, we are aware that this constant is our y-intercept. It's the same way with quadratics. And this value would be our y-intercept as well. So with rational expressions, it's just the constant in the numerator divided by the constant in the denominator. Once again, that's in standard form, and it's a whole lot easier to find it in standard form than factored form, but factored form actually isn't too difficult anyways. So let's take this expression and this rational expression again, and let's now focus on factoring it for the next slide. So x squared plus 7x plus 12 and I think the denominator was something like this. Let me double check. Minus 5x minus 6. Okay, great. And we're already done finding the y-intercept from this rational expression, but the easiest way to find the x-intercepts and vertical asymptotes is by factoring this. So, since there is no greatest common factor in the numerator, we're going to try to use the product sum method for factoring. And oops, I think I forgot a digit here. I think this is supposed to be 7x plus 12. Let's double check. Yep. The product sum method is used when we have a trinomial, a quadratic trinomial. And this last term, this constant, we want to split that up into two different factors. So we have to ask ourselves, what two numbers multiply to give us 12 and they add to give us 7? And once again, the name product sum comes from product, meaning the answer to a multiplication, and sum meaning the answer to an addition problem. So I might say to myself, well, 3 and 4, 3 times 4 gives me 12, and 3 plus 4 gives me 7. So I've successfully identified what my factors are, and I simply write this as x plus 4 and x plus 3, sorry about that. And we use product sum to factor that numerator in this rational expression. And we're going to do the same thing in the denominator. What two numbers multiply to give me -6? And those two numbers should add to give me -5. You might remember there are some different tricks for this, but the two numbers we're going to want to use include 2 and 3, but a positive 2 times a positive 3 doesn't give us a -6. So one of these two terms is going to have to be negative, either -2 or -3. And actually, sticking back at this, if we stick with 2 and 3, let's say that the 2 is negative. Let's just take that guess first. And -2 plus 3, looking here, -2 plus 3, well, that doesn't give us -5. So those two factors aren't going to work. See. So we're going to want to find some more factors. Let's get rid of these. And that deleted a lot. I believe this was 3 and 4, and 3 plus 4, which leaves x plus 3, x plus 4. Sorry about that. The eraser isn't working for some reason on this. So two other factors. We know that 2 and 3 aren't going to work. So the other factors are 1 times 6 and 1 plus 6. Once again, one of these values is going to have to be negative. I see that because this is a -6. So a positive times a positive is not going to give us a negative. So the value we would like to be negative is this 6. And I know that because 1 minus 6 here, 1 plus -6, that is going to give us the -5 that we're looking for. So the factors in the denominator are x plus 1 and x minus 6. Okay. And this is what we're going to use to help us find the x-intercepts and vertical asymptotes on the next slide. So now that we have this in factored form, it's a whole lot easier to find x-intercepts and vertical asymptotes because, similar to our work, what we've done with polynomials, we know that our factors clearly identify our roots, and it works the same with rational expressions. So the one thing I think that's important to remember that is we often forget about is if we have 0 over any number at all, the outcome of that is 0. So what that means is if I can get this factor right here, if I can get this to equal 0, well, 0 times anything is just going to give me 0 overall. If I have 0 in the numerator, then my outcome is going to be 0. So my goal is to get this equal to 0, this factor equal to 0, and then this factor equal to 0 as well. And my outcome will be 0. And if we think back about our work with even linear equations, let's take an example real quick and say y equals 2x plus 18. Well, if I'm thinking about a graph here for a second, I know anything that's going to be on the x-axis has to have a y value of 0. So if I have a positive y, it'll be up here. A negative y will be down here. So when our y is 0, we have our x-intercept. So what we've done in the past is plug in 0 for y, and then we can solve for our x value. So we would have -18 is equal to 2x, and then we can see is equal to 2x, and we divide both sides by 2, and we can see that our x-intercept in this case would be -9. So it's important to remember that whenever we want our x-intercept, we put 0 in for y. That's what we're going to do up here as well. So I want this whole thing to be equal to 0 to figure out my x-intercept. So what I want to do is get this factor equal to 0, both of these factors equal to 0 to find my x-intercepts. So a simple step is let's take this factor, which was found from here, and set that equal to 0. And when I subtract 3 from both sides, you can see that one of my x-intercepts is at -3. And now I take my, and let's check that just to confirm. So I'm saying right now that -3 will make this whole quantity equal to 0. So I'm going to plug in -3 and double check that. So instead of x, I'm going to have -3 plus 3. And once again, that's coming from this location. Instead of x, I have -3. And here will be -3 plus 4 over -3 minus 6, and -3 plus 1. So let's just take it this way for a second. And get the structure set up. So I see that -3 plus 3 gives me 0. -3 plus 4 is +1. -3 minus 6 down in our denominator is -9. And -3 plus 1 is -2. Once again, I just simplified this to give us this. And take it one step further. 0 times 1 is 0. -9 times -2 is +18. Well, 0 over 18 is still 0. So we have successfully proven that -3 will give us an x-intercept. Okay, so we're going to do the same thing. This time, rather than doing x plus 3, we're going to focus on our x plus 4. And we're going to do the same thing. So x plus 4 is equal to 0. Subtract 4 from both sides. Our other x-intercept is x equals -4. So a lot of you have been asking, like, well, I'm not sure when to flip it, right? When I say flip it, you're talking about the factor. This is referring to the factor, and this is referring to the x-intercept. So this is a +3 in the factor, but a -3 for our x-intercept. And the reason for that is when you plug in your -3, your x-intercept, into your factor, -3 plus 3, this simplifies to 0. And that's what we're looking for, is to make sure that our numerator comes out to be 0. Okay. So, in this case, we've identified our x-intercepts to both be -3 and x equals -4. Okay. So, let's record some of this information. Let's go all the way over here and find some open space. So far we have our y-intercept from the previous slide is -2. And we've got our x-intercepts at -3 and -4. And now we're going to find our vertical asymptotes. And the vertical asymptotes are very similar to what we've done. Where are we? Very similar to what we've done to find our x-intercepts in the numerator. The only difference is, this time, we want to focus on a number. Any number over 0 is undefined. And we know that an asymptote is somewhere where we cannot have an x value. It's impossible to have the x value because we can't divide by 0 ever. Well, if this factor turns into 0, then we're going to have an undefined value. And if this factor is a 0, then we're going to have an undefined value. And that's exactly how we find our vertical asymptotes from our denominators here. So we're going to take this x minus 6 and this x minus 1 and find our vertical asymptotes from them. So x minus 6 and x plus 1, excuse me. X minus 6 and x plus 1. Those are our two factors. Notice I'm splitting them up just like we did over here for our numerators. So we have the x plus 3 equals 0, x plus 4, and x plus 4 equals 0. So it's the exact same process. This time we're just using our denominators instead. And to solve this, we add 1 to both sides, and one of my vertical asymptotes is at x equals 1. And my other vertical asymptote is at positive 6. Okay, so our final answer, vertical asymptote, and let's just do this. X equals 6. And it's okay to write it this way as long as you identify that it is a vertical asymptote at x equals 6. Another vertical asymptote at x equals positive 1. Okay, so as long as you write that it is a vertical asymptote, you can write x is equal to 1. Whereas this means something different. You're identifying the x-intercept at these two values. So hopefully that helps finding x-intercepts, y-intercepts, and vertical asymptotes. The main thing to keep in mind is this part right here. Whenever we have a 0 in the denominator, we have a vertical asymptote. And whenever we have a 0 in the numerator, that is going to be our x-intercept. Thanks for watching.